continue from where we had left off in the last lecture. So, we were looking at the different types of temporal operators, namely the operator xp, which says that p is true in the next state. So, that means on a path pi, if we find that p is true in the step following the first state, then xp is true on that path. Then we looked at p until q, which says that p must hold at all states until we reach a state which satisfies q. Then we have the fp operator or the future p operator, which is true if somewhere in future p is true, which can also be alternatively expressed as true until p, because we have true here, true here, true here, and then p. And then we also have the gp operator, which says globally p must hold. So, in other words, if p holds everywhere, then there is no point in the future where not p holds, and that in turn can be written as not true until, sorry, not p, this should be not true until not p, right. So, we realize that these two are the basic operators and the others can be expressed through that. Now, we are going to see our first temporal logic, which uses these operators. So, the syntax is that we are given a set AP of atomic propositions. These are the symbols over which the logic formulas are defined. All Boolean formulas over AP are LTL properties. So, AP is like a set of signals, it is a set of variables. So, all Boolean formulas over AP are LTL properties. So, the complete Boolean logic is contained in LTL, and if f and g are LTL properties, then so are not f, xf, and f until g. So, that completes the definition of the logic. Now, as you can see that in turn this f and g can have other sub formulas. So, you can have f until p until q and things like that. What is the semantics of this logic? So, we already defined the path semantics for xf and f until g and fg and gf, right. Now, the semantics of linear temporal logic is that a Kripke structure K, remember we defined what is a Kripke structure, it is a finite state machine which has a complete transition relation. So, a Kripke structure K models a LTL property G, which is denoted as K models G, if and only if for every path pi which starts at some initial state of K, pi models G. Remember that these operators were defined over path pi, right. So, we can, so the property holds on the Kripke structure if it holds on all paths in that Kripke structure starting from the set of initial states, right. So, this means that the property does not hold on K if there is any path in K which refutes the property, right. So, when we are going to do the verification, we will look for paths which refute the property, and finding any such path means that the Kripke structure does not satisfy the property by this semantics. So, let us take an example here. So, this is a Kripke structure where I have these 5 states S0 through S4, and the labelings of these states with the atomic propositions are given here. So, this is labeled with P, this is labeled with Q, and whichever labels are missing here, we assume that those propositions are false there. For example, P is true here, so Q, R are false here. Okay. In this state, P and Q are true, R is false. Right. So, the false ones are not explicitly written. Now, in this, let us examine the truth of the property P until Q. Now, the property P until Q holds here, because if you take any path, say let us say this path, then P until Q holds. Okay, we must start with the initial state, remember. So, this is the initial state. So, P until Q holds along this path. If we take this path, then we can go here, and then we can go here, and then here P until Q is satisfied, right. Similarly, the property FQ holds here. how does the property FQ hold? If you want, FQ will also hold because of the same reason. Along this path Q holds here, along this path Q holds here. So there are no other ways that you can get out of the start state, right? The property GFQ does not hold. And what is a counter example for that? The counter example is the trace S0, S1, S4 and then S4 forever. So that's this trace. If we look at this trace, then GFQ does not hold. What does GFQ says? That always in future Q will hold. So from every state there is a future state in which Q will hold. Now along this path, in this state in future Q holds, in this state also in future Q holds. Remember, future includes the current state. But when you are in this state, then there is no future state where Q holds, right? So in this state there is no future state where Q holds. So GFQ does not hold, and the counter example trace is this. Now see, the counter example trace is not a finite path, because we are talking about a property like GFQ. The counter example trace is a path which recurs after some time, right? Then let us look at this property, the property P until Q until R, right? So this also does not hold. Why? Because we look at the counter example trace S0, S2, S3, S0, S2, S3. So if it goes around in this loop forever, then it is never going to reach a state satisfying Q until R, because see, these three states do not satisfy R. So if this is the path that it goes in this loop forever, then none of the states satisfy Q until R, right? So therefore this property does not hold on this path, right? So again you see, the counter example trace is not just one finite trace, but it is an infinite path, right? Now when we do verification of these properties, then from the design which we are verifying, we will extract out the Kripke structure. We will extract out the finite state machine model from there, and then the property checker is going to look for such counter example traces. If it cannot find any counter example traces after exhaustively searching the Kripke structure, then it will say that the property holds, right? On the other hand, if it finds a counter example trace, then it will say that the property does not hold on the Kripke structure. Okay, we will see how those methodologies work. Now, in addition to the operators that we saw and the logic, linear temporal logic, there are some additional logics which talk about state based properties, right? They are not path based properties. Linear temporal logic properties, as the name suggests, are linear, so they are defined along paths. Now most of the existing industry standard languages are built on top of linear temporal logic, and there are some features which are called branching time features, which we shall study now. They are supported by some of the logics that are available today, but not all of them, right? And they have limited use also. So let us look at path quantifiers. So we have two quantifiers, A and E. A will stand for all paths, and E will denote there exists a path, right? So when we talk about for all paths, then from this state it means that all paths, right? And when we talk about E of some property, then that there exists some path along which it must hold, right? So this kind of logic that we are talking about now is called branching time logic, as opposed to what we studied earlier was linear temporal logic, that was linear time logic, right? The linear time logics are interpreted over paths, branching time logics are interpreted over what are called computation trees. Okay, they are interpreted over trees. So let's see how do we derive a computation tree. So if you look at this Kripke structure, then I can unfold this Kripke structure like this. So what does it say? When I am initially in the state AB, right, in this state, then I have two options, I can go here or here, right, and then from this state again I can go back to this state or I can go to this state. So AB and C. Okay. On the other hand, if I had gone from AB to this state C, then from there I have no other choice, so it's just this. So this is an unfolding of this graph into an infinite tree. All right, that tree is called the computation tree. A particular run of the Kripke structure will follow any of these paths of the tree, right? And in linear temporal logic, we want to prove the property over all such paths. Now, in branching time logic, we will have properties which will talk about either some path or all paths or combinations of these, right? Not like linear temporal logic, where we have only one quantifier which says that check this path property on all paths. Okay. Now let's see how we use this path quantification. So this is the computation tree, all right, and when we say AXP, we mean that all the possible next states must satisfy P, right. So this must satisfy P, this must also satisfy P. When we say AGP, that means that GP must be satisfied along all paths, right. So far this is no different from LTL. If I just wrote XP and checked it on that structure, it would have actually checked whether along all paths P is true in the next state, so that would have had the same effect. If we had given GP, then it would have checked it on all states along all paths, right. So that would have been equivalent to AGP. So far no difference. Now look at this one, AFP, along all paths in future P. So along all paths in future P must hold. Again, this is not different than saying FP, right. A P until Q means that along all paths P until Q must hold. So along all paths P until Q holds, right. Again, we are still doing things which are like LTL or contained in LTL. Now look at EXP. What does EXP says? It says that from this state there exists some next state where P is true. Now this operator is now E. In LTL it is by default there is an A outside the property. It has to hold on all paths. Here we are saying that it has to hold on some path. So that means that we are saying that there exists some next state of the current state where P must hold. When we say EGP, we say that there is some path starting from that state which satisfies GP. Now note, what we are doing essentially is we are taking a path property and prefixing it by a quantifier, right. So the path property is XP, we are prefixing it by E. In the previous cases we were prefixing it by A, right. And if we say E of some path property, we effectively want that it should be satisfied on some path. If we prefix it by A, the path property must hold on all paths from that state, right. So then we say EGP, so this is some path where GP holds. EFP holds if there is some path where in future P holds. EP until Q holds if there is some path where P until Q holds, right. So far any doubt on this? Yeah. Now we are going to look at some more complicated property, but let us first see the syntax. See, so far we have just looked at one property, we have not looked at compositions of these properties, nesting of these properties. So, let us see the logic first. This is called computation tree logic or CTL. Okay, the previous logic that we had studied was linear temporal logic or LTL, and this is CTL. Given a set AP of atomic propositions, all Boolean formulas over AP are CTL properties. So, Boolean formulas are also CTL properties, and if F and G are LTL properties, then so are not F, AXF, EXF, AF until G, EF until G. Now, see, what this means here is that every path property like XF, F until G must be prefixed by an A or A. Now, remember that in LTL we were allowed to write properties like FGP. LTL was allowing that. Here it is not allowed. You will either have to, you can, these are allowed. AFAGP is allowed, AFEGP is allowed, right? You can write EFAGP, no problem with that, or EFEGP. These are perfectly all right. But this, where this path property is not prefixed by an E or A, is not allowed, right? We will see that this makes a lot of difference. The requirement that every path property must be prefixed, every path operator must be prefixed by an A or E, makes the checking of such properties much easier, right? Now, we can also have derived properties like EFG, AFG, EGF and AGF. Right? So, we can have these kinds of properties. I mean, where instead of using the basic temporal operators x and until, you use the F and the G operators. The semantics is as follows. The property AF is true at a state S of the Kripke structure if the path property F holds on all paths starting at S. The property EF is true at a state S of the Kripke structure if the path property F holds on some path starting at S. Okay. Rest of the semantics is just like as in LTL. Let us look at these nested properties. AXAGP says that from all the next state, P holds forever along all paths. Right? AXAGP. So, what would it look like? That if this is my start state, the state on which I am checking AXAGP, then these are suppose the two next states, 2 or 3 whatever next states, then this must satisfy AGP, this must also satisfy AGP. So, what does it mean? That P must be true here, P must be true here, P must be true here, and actually on the whole subtree everywhere P must hold. Similarly, P must be true here, and on the whole subtree here P must be true, right. So, that is what is meant by AXAGP, right. Then if you look at EXEFQ, there exists a next state from which there exists a path to a state where Q holds. Then AGEFR, from any state there exists a path to a state where R holds. So, this says along all paths in all states EFR must hold. That means that in every state of the structure EFR must hold. So, from every state there must exist some path in which R holds in the future. Let us look at some more examples. This is a computation tree which has two types of signals, namely request and grant. Okay. From S, the system always makes a request in future. So we are asking that is AF request true, and what is the answer? True, right? Because if you look at along every path, then in future request is true. Along this path request is true here, request is true here, right? All requests are eventually granted. So AG request implies AF grant, which means wherever in whichever state you get a request, then from that state there has to be grant along all paths. So let us look for states which satisfy request. From here all paths satisfy future grant, from here also all paths satisfy future grant, from this request all paths satisfy future grant, from this request all paths satisfy future grant. This also is hold, this also holds, right? Sometimes requests are immediately granted. There exists some path in the future where request is followed by the grant in the next state. Is this true here? Yes, and an example is this path, right? Now how do we say that this holds? So this one satisfies request, right, and EXGR also, right? So we have EF along all paths, request implies EXGR, right? Now see, there is a slight bit of problem with this property. Suppose there is a path where request is, let us take this state for example. This state does not satisfy request, right? This state does not satisfy request. So request implies EXGR is true here. Yes or no? This property request implies EXGR is true here vacuously. What is this request implies EXGR? It is not request or EXGR. I can break up this property and write this as not request or EXGR. But then not request is true here. So this sub property is true here. And then I can say that look, here is a path where in future this sub property holds, right? So we did not actually check that the request has come. So probably we should have added EF request and EXGR, right? So not the implication here. Probably this should have been the AND. Right? Then you are forcing that there should be some state in the future where request holds, and from then EXGR must hold. So then that will not allow things like this, but it is going to pass because of an actual request grant sequence like this, right? So this is just to give you an idea that when you write properties, if you make mistakes, you might feel a sense of confidence that I have written property and it has passed, but actually you have not checked anything. Requests are not always immediately granted. So you want to check that it is not always the case that the grant comes in the next cycle, right? So you are saying that not AG request implies AXGR, right? And look at this one, this is a request right, and we don't have AXGR here, right. So, this is a state where we have request and not AXGR, right. So, this is a state where this part is false, right. So, if this part is false, then we can say that not AG of this is true, because AG requires that this should be true everywhere. Right? We are just learning to play with these operators. Requests are held till grant is received. So, this says that along all paths globally always requests implies that along all paths request will be high until grant. So, once you have made a request, you will hold the request until you get the grant, but it also says that the grant must come in the end, right. So, now is that the case here? So, you look, wherever we make the request, we hold it until the grant comes. Here also we hold until the grant comes. Here the request is held until the grant comes, right. So, this part is actually true everywhere, and it is true vacuously in those states where request is not true, right. So, it is vacuously true here, it is vacuously true here, it is vacuously true here, okay. So, that is how this whole thing holds. Clear? Now, let us get a little bit of insight about what is the difference between this linear temporal logic and computation tree logic. What is the difference between LTL and CTL? Now, CTL has more operators than LTL, which allows us to specify branching time properties which are not supported in LTL. So, no issues about that side. The question is, can all LTL properties be expressed in CTL? Now, we know from the syntactic point of view, FGP cannot be expressed in CTL, because you have to prefix every path property with an E or an A. So, we said that EFAGP is fine, but FGP is not fine. Now, you might say that the same intent as FGP is captured by some equivalent CTL property. So, for example, one might be tempted to say that why is FGP not equivalent to AFAGP? What does this say? This says along all paths in future we will reach a state from where P will keep on holding forever, right. So, GP means P holds forever in future, and FGP means that we must along every path we must reach some state from where every successive state, all other states must satisfy P. So, GP holds on this part, and there must be some state x in future which satisfies this GP. So, x models GP on this path, and that such an x must be there in all paths, right, from where in future P holds. You might say that why is this not equivalent to AFAGP? What does AFAGP say? That along all paths in future there must be some state from where everywhere in future P will hold, right. But actually this and FGP are not the same. So, to show that these are not the same, we will take one example here. Look at this script case structure. We have S0 where P holds, and then S1, then S2 again where P holds. Now, if we open this up into its computation tree, then this is how it is going to look like. So, this is the S0 state, S0, S0, S0. So, from S0 I can stay in S0, or I can go to S1 which does not satisfy P. These are the S1 states, and then I end up in S2 where P holds forever, right. Now it is easy to see that this satisfies FGP. You take any path, if you take this path, then P holds forever in this. If you take any of these paths, then you reach some state from where GP holds forever, right. So any path that you take in this computation tree satisfies FGP, but does this satisfy AFAGP? Can you give us along all paths a future state from where AGP holds? No. Why? Which is the path which cannot give us that thing? This path. See, in this path, if you go down this path, this is which path? The path where you stay in S0 forever. You keep on going in this loop forever. So in that path, you see there is no state where AGP holds. Does AGP hold here? No, because this state does not satisfy P. Does AGP hold here? No, because this state does not satisfy P. So none of these states satisfy AGP. So AFAGP does not hold here. Right? Now if you put in some more thought on this, you will see that this property cannot be expressed in CTL at all. There is no way that you can express it in CTL. Right? So these two logics are such that none of them is contained within the other. You cannot express properties of one logic completely in the other one. Now let us start with a simple case study to demonstrate the task of developing a set of assertions from a high level specification. So we start with the example of a memory arbiter. So the memory arbiter has two request lines and two grant lines. Now the arbiter has the request lines, typically one is from the processor and the other is a direct memory write from the peripherals, right. Now typically what happens in such arbiters is that the high priority line becomes active only once in a while and that gets priority. So the high priority request is served as early as possible, and when the high priority request is not there, by default the low priority request gets access to the memory. Now between the processor and the peripherals, can you tell me which is the high priority one? No, it is the other way around. See, the processor is going to use the memory all the time, right. So it is the default user of the memory. It is the peripheral which is going to transfer data in burst mode to the memory once in a while. So it is going to have priority, the CPU is going to stay back, allow that transfer, and then again the grant will come back to the CPU, right. So it is that way. You get my point? Now the properties that we want to implement here are as follows. The request line R1 has higher priority than request line R2. Whenever R1 goes high, the grant line G1 must be asserted for the next 2 cycles. So we are assuming that the high priority request requires 2 cycles to perform its transfer. So the grant should be high for at least 2 cycles. So we write that in LTL as always R1 implies next G1 and next G1. Then we say when none of the request lines are high, the arbiter parks the grant on G2 in the next cycle. So when we have not R1 and not R2, none of the request lines are high, then in the next cycle we gives the grant to G2. The grant lines G1 and G2 are mutually exclusive. So, because we cannot give both of them grant at the same time. So, the mutex property is written like this, always not G1 or not G2. Okay. So, these are the three properties that we start with. Now, the first question that we ask is the specification correct? Because you will see that often when we write these properties, there can be inherent inconsistencies, right? And actually there is an inconsistency here. And what is that inconsistency? Let us consider the case when R1 is high at time t and low at time t plus 1. Right? So, at some time t, R1 is high and then it goes slow. Right? Now, what does this property says? This property says that in the next two cycles, G1 must be high. So, it must be high in the next cycle and it must be high in the next to next cycle also, right. So, it must be high in two consecutive cycles. Now, let us see what this one says. Now, let us look at the situation here. Let us say that the other grant line R2 is always low. So, it is always low. Now, if you look at this cycle, then R1 has become low, R2 is also low. So, this property requires that G2, that is the other grant, should rise here, because in this cycle we had both R1 low and R2 low. So, G2 must be high. Now, see the problem here. In this cycle, therefore, the first property requires G1 to be high, the second property requires G2 to be high. But then the third property says that two of them cannot be high at the same time, right. So, there is a conflict here. This specification cannot be satisfied. This is an unsatisfiable specification. Now, you know about the SAT problem in Boolean logic, where you are given a Boolean formula and you are asked to verify whether it is satisfiable at all. This is a question of temporal logic satisfiability. So, in every logic you can write properties which are unsatisfiable. This is an example of temporal logic specification which is unsatisfiable. Right? Now, if you have an unsatisfiable specification, none of your implementations will satisfy that, because it is unsatisfiable. So, we need to go back and change the specification. Right? So, let us see. Now, where was the problem? This was fine. This is what we actually want, that whenever the request line is high, grant must be high for the next two cycles. No questions asked about that. The second one said that when both are low, then in the next cycle G2 should be high. We want this to happen when it is not already committed to give G1. The problem there was that we had R1 true in one cycle, and in the next to next cycle we were already committed to asserting G1, but then this one forced us to also assert G2, right. So, we can say that, well, to express the same intent that the default grant goes to R2, we can say that whenever we are not asserting G1, let us assert G2, right. We are not asserting G1, so let us assert G2. So, that way we get around that problem. We want to park the grant by default on G2. So, that is what is happening here. In whichever cycle G1 is not granted, let G2 have the grant, and let this be the case. Right. Now, these three properties together is satisfiable, but we have another problem, and the problem is the specification complete? Now, you see that there is a peculiar situation. Now, we can satisfy all these properties by designing an arbiter which always asserts G1 and never asserts G2. See, if you keep the grant always on G1, then see This property will hold always, because anyway G1 is true in next G1, everywhere where G1 is true. This is also true because there is no state where not G1 is true, G1 is always true, so this is true by default. And this is also true because we are always asserting G1 and never asserting G2, right? But that's certainly not the implementation that we want. So this is what is called the completeness analysis of the specification. We have to find out whether the specification is complete, in the sense whether we have sufficient number of properties to express the design intent. Here certainly we do not have sufficient number of properties. So we need to add either of the following two properties. We need to add a property, either one which will specify when G2 should be high explicitly, that this is the scenario where G2 should be asserted, or it should be one which specifies when G1 should be low, right. So let us go back to the specification. Now we add a new property which says when R1 is low for consecutive cycles, then G1 should be low in the next cycle. So this is specifying that when G1 should be low. So if we have not R1 and X not R1, then this will not hold anymore in the next to next cycle. So there is no compulsion, this will not give you any compulsion for asserting G1. So in that case we must assert, we must lower G1. So if the request was not high in the previous two cycles, then lower G1. Now when you lower G1, this property automatically means that you assert G2, right. So by specifying when G1 should not be high, we are also indirectly specifying when G2 should be high, because G2 is the default grant, right. Is this complete now? Now see, there is still a funny thing out here. We can satisfy this specification without reading R2. Now look at the specification here, that we have these four properties. Can you please switch it to the computer? We are having these four properties, and we cannot satisfy the specs without reading the value. We cannot satisfy the specs without reading the value of R1, but we can satisfy the specs without reading R2, right. So without reading R2, what are we doing? We are asserting G1 whenever R1 requires G1 to be high, and in all other cycles we are asserting G2. So what is the point in reading R2, right. Now in this case maybe we would accept this, that okay, we actually do not need to read R2 because G2 is the default grant. So the low priority device does not have to explicitly put in a request, right. Whenever it has the grant, it uses it, as simple as that, right. So we live with this specification. Now the next thing that we are going to look at, okay, so this is all giving you a flavor of the problems that come up in specification development. The next challenge that comes up is that a lot of properties are real time properties. So far when we said that something will happen in the future, we did not specify how far away in the future. Is it going to happen in the next 2 cycles or in the next 2000 cycles? If we say f of p, it does not specify that how quickly p is going to happen. But in reality, if you look at controllers for aircraft, industrial machinery, robots etc., there is a requirement for specifying real time properties. So one option is that we use the X operator. So suppose instead of saying that event p will happen in the future, suppose we want to say that event p will happen within at most n time units, we can write p or xp or xxp or n times xp, right. Now it is painful to write the property like this, particularly if your n is quite large, right. So what we do is we annotate all our temporal operators with time bounds, right. So this is called the real time extension of the operators. So when we have G, M and P, it says that P always holds between the mth and nth time step. In all holds in all states between the mth and nth time step. F, M and P means that P eventually holds between the mth and nth time step at least once between the mth and nth time step. Right? Here it must hold in all states between the mth and nth time step. Here it must hold at least once between the mth and nth time step. XMP says P holds at the mth time step of the path, and P until M and Q means that Q must hold sometime between the mth and nth time step, and P holds in all states until that state where Q holds. Right? This one, it must hold. So suppose Q holds in the jth time step where J is between M and N, right? Then in all states up to J, P must hold. Right? We are going to see examples of this. So here, see, this is G24P. So from all cycles, from the second to the fourth cycle, P holds. F224P, that it must hold sometime between the second and fourth this thing. So it holds here, so that's fine. So X3P, it holds in the third cycle. P until 24Q, so it holds in the third time step. So 3 is between 2 and 4, and then P holds in all states preceding that state. Okay. So this is an example of some branching time properties using the real time operators. So this logic is called RTCTL. Actually, this is a slight extension of RTCTL because you have these passage things. So what it says is that always whenever HP request rises, then around each path within 4 cycles the grant should come. So whenever HP request is raised, within 4 units of time HP grant must be raised. The second property says Arbiter will provide exactly 64 units of time to high priority users in each grant. So when the HP using is the time when it starts using the resource. So whenever that rises, then along all paths we will have not negate HP using, which means that HP using will not fall until the 64th cycle, and after that HP using will fall. So this says that HP using is held high until the 64th cycle where HP using goes down. So that expresses this intent that it gets exactly 64 units of time. Right. So we will stop this particular lecture here, and in the next lecture we are going to start looking at the industry standard extensions of these languages. So there are some languages which have been adopted by the industry. These are logics. These are the logics based on which the industry standard languages have been developed. So in the next lecture onwards we are going to study one such standard.